Okay, we're going to be looking at electronegativity. Now last year you had to know what electronegativity was, so definition, and you had to use it to determine if a bond was polar or non-polar or whether it was ionic. You still need to be able to do that this year. But what's more important is describing and justifying the trends on the periodic table. To do that, you need to know what electronegativity is. So just very quickly, electronegativity is a measure of the relative attraction for bonding electrons by a particular atom. And we measure it on the Pauling scale, which goes up to 4, and the most electronegative element is fluorine, which has a value of 4.0. That means that fluorine has got a very strong attraction for any electrons when it's in a chemical bond with another atom. So the only other atom that really has what we call a non-polar bond with is another fluorine atom. It's that electronegative. So just to summarise, we're looking at bonding electrons, we're looking at a relative attraction, so relative to the other atom, and it's measured on a thing called the Pauling scale, which goes from 0 to 4.0. The thing that helps us determine the trends on the periodic table is the effective nuclear charge. It's not just the number of protons, it's the number of protons and how far away the bonding electrons are from that nucleus and how much shielding there is from other electrons at lower energy levels. So those three things come into it. And what we find is the trend is that as we go down a group, the effective nuclear charge is actually getting smaller. So therefore, the electronegativity is getting lower. And as we go across a period, we find that the electronegativity gets higher. This is because you're getting more protons in the nucleus, so you're getting a stronger positive charge there. So the things that we have to look at for the effective nuclear charge, as I sort of said just before, are the number of protons. We need to know how many protons are in the nucleus. If that number keeps getting bigger, you would expect there to be a bigger pull on the bonding electrons. However, that's not always the case. Fluorine has fewer protons than chlorine, but it is considerably more, or it has a considerably higher electronegativity. And the reason for that is that chlorine's bonding electrons, or valence electrons, are at a higher energy level. They're in the third energy level, not just the second. So for a start, they're further away from the nucleus, so the actual pull of those protons will be diminished because of the distance involved. But as well as that, there is the shielding of the 1s orbital, and then the 2s orbital, and the 2p orbital. All of those electrons shield some of that positive charge sort of getting through, a bit like a filter. So not all of the 17 protons of chlorine are actually attracting those valence electrons to their full potential. They're actually being shielded by lower energy levels. So we find that the actual distance is not an effect, so the radius of the atom or the radius of the ion, and shielding by electrons at lower energy levels. So if you can use these three ideas, you can write quite concise, quite good definitions, justifications for why electronegativities decrease down a group and increase across a period. And that's really all you need to be able to do. One thing that is quite nice to link it to, if you look at these ideas here, is link it to atomic radius, which we did in the previous lesson. So you can actually use atomic radius, so the distance is involved, as one of your starting points. Right. And that's really all you need to be able to do with electronegativity. You need to use it, of course, like we did last year, to justify bond type. Is it ionic? Is it covalent? And if it's covalent, is it polar covalent or non-polar covalent? There's some numbers to remember there. And then you need to know the two trends and to be able to justify them in terms of effective nuclear charge, which means in terms of how big the nuclear charge is, how far away those valence or bonding electrons are from the nucleus, and how much shielding there is, so therefore how much does that diminish the actual effective charge. I'll stop there.
Okay.